Okay, we'll go ahead and get started. We think we have critical mass. We'll have a few more folks coming in. So the focus to this point has been primarily business and how to relate to the business, communication techniques, understanding the differences between how business stakeholders think, how technology stakeholders think. We walked through the accounting concepts. We spent quite a bit of time on technical debt and how to repay technical debt, persuading others why they should pay for technical debt. And ultimately, we want to get product managers understanding that. Right before the holidays, we talked about organizational design. This was about the reasons for small, durable, autonomous teams, how they generally improve innovation. And then the last session, we went through OKRs, outcomes, and key results. So the supporting slides have additional examples in there for you to look at. So the focus for the next 5 sessions would be more around architectural concepts. They'll be high level, but we'll start with really availability for really the first 3 sessions. Let's get started then with today's session. We might get done a bit early today. This all comes from a services mindset, and we'll walk you through what we mean by a services mindset. Traditionally, IT was more project-based or more we used to ship products. So the idea of a services mindset is that software as a product, and this is B2B, B2C, there is a license, you pay for that. But software as a service is a subscription. So it's that renewal, completely change the buying process, completely change the support process. Almost everything you get now that you purchase and make money on is a subscription service versus the pay up front and then a 20% maintenance fee. As we thought of this, we used to ship products. Now we are shipping and actually managing a service. It's a different mindset. Really, software, as we used to think about it, as you send someone the CD or they download the installation files, that's becoming less prevalent because customers aren't buying that, they're buying the service. So we want you to think of this as a ubiquitous utility that's available to everyone, even for those of you that are operating only in North America, only in the United States. It's a utility available to everyone. It's really self-service, so the sales process is easier. There should be low friction sign up. It's all configuration versus customization. But the takeaway is that you're a utility business. You're delivering a service. So it's a very different mindset than you ship it, let other people worry about availability, about the maintenance, the upgrades. You are managing all of that from end to end. For companies that are going through this, older companies, those that are typically 2 decades or older, they have to go through this mindset shift. And for those of you that are newer companies, you may still have leaders or stakeholders that are still thinking in the shipping software versus managing a utility or a service. For years, for decades, going back to the 70s, we thought of this as a manufacturing process where you would ship something out the door. You would have these long release cycles, where now it's a continuous delivery process. High availability was typically an afterthought. Your customers would think about that through infrastructure, or even some larger companies we've seen, they still think of infrastructure teams managing high availability versus high availability is just the table stakes, should be designed in the solution. It should be a feature managed by product. Instead of responding to customer reported problems, when you manage utility, you have to identify them before the customer does, monitor them, detect them. You don't want to be the last one to know if you're managing your service. Additionally, instead of allowing customers to self-service and let them deal with local issues, you have to now think about where your customers are globally and be able to act fast no matter where they are around the world. We won't get into this as much today as we will in some future sessions, but thinking about how do you manage a service in multiple continents and provide high response times and high availability across continents. Moving away from customizable, tailored solutions. Remember, in the past, you would ship software. The software would follow a 3-year release cycle, sometimes a 4-year release cycle. When you would take on one of those releases as a buyer, you would typically make some customizations because it didn't fit your needs. And then you would get the next release several years later. You couldn't take that first release because you'd made some customizations. So you would typically work on a patch. So by the time you actually use some software in your environment, whether it was commercial or whether it was personal use, even like Microsoft use, that stuff was on the drawing board 4 years, sometimes 5 years before, where now you're basically rolling features out all the time. It has to be simple, highly configurable, one code base for all your customers, make it extensible for your customers via APIs versus you managing those extensions. Very different mindset shift when you're delivering software as a service, again, whether it's consumer facing or commercial facing. We talked about those massive revolutionary product development cycles. You'll still see this in some companies. They still follow this 3-year, 4-year cadence. They just couldn't break that versus you're moving towards this iterative, evolutionary, very fast A/B testing where you continue to release things. We still see some larger companies that have the ability to roll out things every day, every month, but they still tend to follow more of a monthly or an annual cycle just to manage all of the upstream and downstream effects of I want to market the software. I want to get some PR out there. I want to get my customer support team ready. I want to get my channel partners ready. So you still may follow this cycle because you have so many humans involved, but ultimately you're shipping something very quickly and be able to update multiple parts of your code base or your service. And then lastly, instead of letting the clients have very specific things on their terms where they have to get all the leverage in a contract just to win a deal, the idea is you can manage multiple groups of tenants and you're producing that yourself. So it's a very big mindset shift. I'm going to pause here for those in the audience. How many of you, by show of hands, think you operate more on the left side and want to be more on the right side? How many of you feel like you're missing some of these aspects on the right side? So by show of hands, got quite a few hands there. Does anyone want to come off mute and explain their challenges? Perhaps Stephen, where do you feel you're missing?
So I think one of the big one that jumps out to me is the extensibility aspect. I think at my company, that is an afterthought, and there is effort to change that, but definitely not there.
Are you tailoring to customers today or just, providing bespoke solutions for them or trying to fold those into the product, or how do you address that today?
Today, there are APIs and a few ways. We have it's like a scripting product and a few customizable solutions that allow customers to build on the platform to some degree, but it's a very small subset of the functionality that they can build on. So yeah, so essentially the company or our solutions engineers are the ones doing the customized work for customers.
Do you have a product manager that manages your APIs?
Yes, we do.
Okay.
Yes.
Yeah, and they have a very different persona they're serving, right? It's a very different market. That's typically when you first introduce that role, it's a different mindset, and to have a product manager and a team just focused on that capability at that level. All right, I saw one other hand raised. Christopher, did you want to share your thoughts? That's okay if not.
Oh no, I'm happy to. Yeah, I guess right now we're still trying to test out if we can get to the right as well. So a lot of what we offer is kind of bespoke project work. Like our offering is very technology led, being that we're kind of in the language AI space,
Mm-hmm.
and we work with biotechs and pharmaceuticals. But a lot of like what they're asking for are more kind of pinpointed. It's very like a project-based service type approach right now, and I guess, and it works obviously because it obviously generates revenue for us. But is there a way to, I guess, lean out that offering so it's more kind of like, do they want to use their own data science teams to interact with, say, in an API based way, or more automated dashboards and stuff? But right now it's very much they kind of ask the questions and our data scientists will use our analytics and stuff to answer those questions for them and present it in a more report based fashion. So I guess a lot of it's just us trying to figure that out, if that's if we can, if they would use it to the right, because they use like other social listing software platforms, but it's more like brand health and that type of social listening aspect. Ours is more in the kind of rare and chronic disease space where people, these pharmaceuticals are trying to understand like lived experiences and stuff, and those platforms can't really drill down the way our analytics are kind of fit for that type of purpose of analytics, but it's very much service based in that regards.
Yeah. Where we typically see companies need to expand more of an API approach is if you have a large services team internally, or you have a large channel of outside consultants that are more technical that are doing this work. That's when you start having to scale and push more of that API level to that larger workforce. It's not just at your customer base, but the channel partners that are working with you, or a professional services team that's doing that work. In your case, it may be data scientists. So you just may not be at that tipping point yet. And that can be, just start thinking of those humans involved that are doing that, where it makes sense to shove more of that to them to self-service. So good answers, everyone. Thank you. So before we get into availability, I just want to step back from an architectural impact, just their impact on the business. And we teach this in there's kind of three big buckets. There's potentially a fourth, security, but we're just going to address really three for the focus of the next few sessions. So one is scalability. That's our background. That's where we came from at AKF. But the idea there is, how can you quickly deliver capabilities to anticipate and meet market demand? So how quickly can you scale your service, your team, your product? That's on the right side. Availability is preventing and mitigating the risks and failures that you're going to eventually lose market share if you have too much downtime. And so those two are kind of related. If you can solve one, it'll help you with the other. And the third is cost effectiveness, which the idea there is make a profit that's significantly better than your competition. And all of this is tied deep into your architecture. It's not always the time or the opportunity that you get to solve all these problems at once. Most decisions that you're going to make on a day-to-day basis are going to focus on one particular area of your architecture. And if you don't understand the other two areas, you can make a decision at the expense of the others. And we'll walk you through those, particularly on cost. For example, you could try to improve availability, for example, by adding a lot of redundancy. That could increase your cost structure and may ultimately impact your scalability. Some decisions that you make get to address two areas. It's very rare that you get to make decisions that help all three areas. Now, the idea is that you need to have engineering and product in the business work together so that you can identify high-level principles that are focused on outcomes for your business. These outcomes should be related to cost effectiveness or availability or scalability. The principles, and we'll talk about that just briefly, architectural principles that are embedded within each of the working teams, and then you as a leader to basically use these principles, enforce it, but really to make those teams autonomous and self-service and really be as autonomous on their own. So we're going to hit these principles in a later session, but generally some of these, we're just going to hit these quickly. Using commodity hardware, buy when non-core, don't build something when you can easily buy it, use mature technologies. For scalability, designing from multiple active sites or independent releases so that you're not impacting one set of customers versus another. And then availability, we'll walk through these. Designed to be monitored, crawl, walk, and run. That means just introducing just as little bit as possible versus trying to have a huge release. Designed for rollback, designed to be disabled. Thinking from the customer back, not necessarily from the engineer forward, and isolating faults so that if one thing breaks, it doesn't bring everything else down. Asynchronous design is around cost and availability. We'll walk you through what N+2 is and our scale cubes in a later session. But right in the middle is when you get to microservices, stateless services, really focusing on automation of our people. When you get to that point, you can actually simultaneously improve your cost, improve your scalability, and improve your availability. So again, we'll walk through these principles later, but just to kind of get a sense of how these different principles apply to your outcomes of cost effectiveness, availability, and scalability. From those three, we like to start with availability, because if you can understand the risks around availability and how to solve those risks, it makes it much easier to improve cost effectiveness and improve scalability. So let's look at availability risk, and we're going to talk about just simple downtime. Let's say a service is down. The risk of a service failure has really two components. There's the probability of an incident multiplied by the impact of that incident. Okay, standard stuff. What's the likelihood and what's the impact if this thing does go bad? For the impact of an incident, there's the duration on the right side. How long does it happen? But also what percent of customers are impacted? Are all of your customers impacted? And then what percent of transactions are impacted? Does all of the functionality of the service working, or are some components not working? So ultimately, how long, how many people were impacted, and what of the service that they're trying to do was impacted? So that's another factor there. From duration, this is when you get into time to detect there's an incident, time to isolate what the problem is, and then restore service, and then ultimately the time to resolve that. A lot of clients that we work with are only tracking one of these activities, duration. They're not necessarily tracking TTD, TTI, TTR. Those are the time to detect, time to isolate, and time to resolve. Your ability to resolve really falls back on how fast can you roll something back if it's something you did, how quickly can you disable something, or in the event of a disaster, what's your recovery point and what's your recovery time. When we get into time to detect, that is business metric monitoring, which is a bit different than system components. So system component monitoring is CPU, memory, perhaps maybe seeing a specific query is slowing something down. Business metric monitoring is starting to see the impact at a service level from a customer perspective. Things are starting to slow down. This is going to indicate things are backing up and there's going to be a problem. So this is where these pieces fit in together. So that's all the right side is the impact of an incident. Pretty straightforward. Probability is a bit more complex, and not all of these are, but the first one is components and call chains. We're going to break this tree out quite a bit more. But the next is the release size, which is how big a change are you making to your environment. If you have a large monolith, you're probably changing the entire code base at once. If you're doing a database upgrade, you might be on a monolith. You'll probably have to take an outage for everyone. And then testing is the amount of testing that you can do, whether manual or automated. Obviously, you want to automate as much as possible. All right, so release size, again, pretty straightforward. Testing is pretty straightforward. The components and call chains is one that we find a lot of our clients don't quite understand until we walk through this tree. So when we say components and call chains, there's the availability of each component by itself, and tightly coupled to that is how those components talk to one another back and forth. And we'll walk you through some examples for the rest of this particular webinar. Availability is impacted by the age of each component. Old items generally tend to have a higher likelihood of failure. The maturity also, if it's a recent release, there's a common thing, in particular in the hardware world, called infant mortality, where new items tend to fail more frequently. Then there's the cyclomatic complexity of each component. How much is each thing being asked to work on? And then, how much does it have to do for every single call? And then the workload demand. Where's the bottleneck in a particular service of what's getting constrained? Is it memory? Is it CPU? Is it disk IOs? Where is that particular demand? So all three of those relate to the availability of each component. The component to component has a few aspects. One is just the network distance. So how long does it take to go? Because the further it goes, it's probably making more network hops. That increases the probability of failure. The payload size, the number of calls, that's a chattiness back and forth. And then the nature of those calls themselves. How many of those are calls in series versus calls that behave in parallel? So in series, think of it like a phone call. Everything has to be live and talking to one another. Asynchronous is more like a text message back and forth. How you mitigate calls in series versus parallel is going to be mitigating anti-patterns. Our next session webinar is going to go just drill down into that. And then this is fault isolation architecture. We're going to talk about our cube concept. That will be the session after that. We walk through our scalability and availability cubes. But how can you design your architecture where it's fault isolated? So generally, these items on the left are architectural decisions. Generally, the items on the right are process decisions. So this requires your management and your leadership skills, but also your architectural skills, because a lot of these aspects fall on different parts of your team and different parts of your organization. So let me pause there before we move to the next slide. Any questions about this risk model? All right, no questions. So this is just a restatement of those. We're going to walk through this first one in more detail, but availability of components. Hardware typically has higher availability than software. It's very hard for software to exceed 4 nines of availability, and we're going to walk you through that. Interactions of components, again, what you want to look for are things that behave in series. Those are the bottlenecks. Those are going to kill you from an availability perspective. And then latency can also lead to queuing, which will cause bottlenecks. Payload size, in that case, it's the smaller the change that you're going to do in production, the smaller the risk. So try to launch smaller batches of code, test it more often. That's going to reduce the probability of an incident. The testing coverage, how much you can automate from unit testing, integration testing, code reviews, automated functional testing, all of that's going to reduce the risk of defects. Fault isolation architecture, again, isolating by service or by customer helps limit the blast radius. That can also lead to quicker time to detection also. Monitoring, as you're releasing new features, think about how are we going to monitor this? How are we going to know if something's happening? Real-time metrics we talked about is trying to identify where it is. So always think about how you're going to monitor the solution from a system level, but also from a business level. And then always have a plan to roll back anywhere in that release cycle. Be able to disable or wire off new functionality, and in particular, be able to make sure you can successfully roll back database changes. Those are the ones that tend to get people in trouble. People tend to roll forward. So now we get to do some fun math for everyone, and it's really understanding availability and the cascading risks of failures. The reason we like to teach it this way is that we found it's not widely understood by software as a service engineers or leaders. It's really not taught in a lot of classes. Some EE classes, some computer science address it, and the real accurate availability math is very time consuming and complex. So we're going to teach you some shortcuts. It's not 100% accurate, but it's 99.99% accurate. Just by show of hands, how many of you were taught availability in undergrad or in your job? Eric, what was besides your job, I assume, did you know that before your job? Did you have that as an undergrad?
No, I learned at AKF.
Yep. Very good.
We're generally taught how to succeed and never really consider how to manage failure. And that's really the point of this entire hour with us.
Our leaders that started AKF, they took a little bit of this in computer science with their PhDs, but for most of them, they learned this on the job too. One of them spent some time at Motorola. And when you understand cellular networks and devices, the network itself, you really have to think through this, because that has to behave like a synchronous call, but you want to make sure you operate asynchronously also. So that's where a lot of these insights came from. And so certain industries, they have to know this, particularly cellular networks or a lot of telecommunication networks really have to understand this. One of the next things you want to make sure you understand is distributed systems. As you start to split your monolith into microservices, can actually decrease availability if you don't design it correctly. The main reason is that you have multiple components that have to talk to each other. The more things that you have talking to each other, the higher the likelihood they're going to break. And so when you work across teams, then you lose the visibility and responsibility of particular services. We also find that unless you're experienced, you may not be able to quantify the likelihood of different availabilities. Not all of your engineers understand the difference between 2 nines, 3 nines, and 4 nines. We're going to walk you through that math real quickly. For those that understand the likelihood, they may not understand or be able to identify anti-patterns that impact availability, and they may not be able to understand the risk profile. Again, so when you split this across teams, no one's really owning the probability or the impact or blast radius. So that's the concern of highly distributed teams. And you want to ultimately design your architecture where teams can operate independently, but one team cannot impact another team. So the way we like to teach this is, and this will be the key takeaways at the top, it's almost impossible to design a single system to get higher than 4 nines. We're going to walk you through that math, why that's the case. The punchline is it's really due to the number of subcomponents that all have to operate just for a single service to work. Then we want your teams to understand 3 things. So translate the number of nines into downtime in minutes or hours, and then into dollars for your service. We also want you to be able to very quickly identify anti-patterns that reduce the number of nines. So we're going to walk you through a lot of anti-patterns in the next session, but every one of those, we bring those up because they're going to reduce your nines and ultimately cost you money. And ultimately, you want your team to understand the risk profile of all your services. And then lastly, so how do you mitigate the risks? So we're also going to walk you through patterns in the next session that help you understand that, and then the basic trade-offs for each of those. So we're spending a lot of time on this session today because we're going to spend almost an hour in the next session to understand anti-patterns and patterns. And we'll walk you through why, but ultimately it's downtime. It's killed us in the past on our prior jobs. We see it impact all of our clients, and we want to make sure you understand the math behind this. So some quick math. When we talk about availability, this is really uptime in just terms of time. We're going to teach you some other concepts about measuring. Some uptime is better than other and quantifying, the ultimate customer impact. But in this case, we're just talking about clock time. So uptime, availability is just the total time it's available over the total uptime and downtime. Mean time between failure, that's the average time between those. Mean time to restore service, how long does it take you to recover? And then your failure rate is just your downtime divided by mean time to restore service. So simple math down here, 4 outages, for a total of 3.5 hours. That availability is 99.96%. And since you had 4, your average one is just under an hour. And your failure rate, again, comes back to that is 4 outages per year. Okay, simple math here. We'd like you to take away either one of these 2 and just be able to know these very quickly. So either know annual or monthly. And this could be for you as a team, but ultimately you want to be able to communicate this to your heads of product, your CEO, your CFO, even sales, to understand the impact of availability. So 2 nines is 4 days of downtime in a year. 3 nines is 9 hours. 4 nines is only 1 hour of downtime. 5 nines means you only have 5 seconds of downtime in a year. Monthly, some people like to use the monthly number because it's simpler math. It's 400, then it's 40, and then it's 4. Okay, so the difference between 2 nines and 4 nines is either 400 minutes or 4 minutes. Good question in the chat there.
Let me read the full question, just
Yeah.
so the folks who are there. Do you distinguish between scheduled maintenance and downtime? My experience with manufacturing systems, we normally would do our maintenance on a Saturday evening, late, sometimes Saturday midnight to 2 or 3 in the morning, when there was nobody using the systems anyway, so we got free time. A lot of those things are no longer available because you've got global customers that are starting to work 24/7 around where we are.
Well, we would like you to design for total calendar time. A lot of you are in a business where you can get away with scheduled downtime, but we'd like you to design for the customer perceived 0 downtime. So we want you to understand the math as if you're trying to provide this service at 4 nines. So we would prefer that you design or think of designing your systems this way, even if you don't deploy this way. But if you can design for no scheduled downtime for your customers, that would be our preference for you. So it's really total time in a year. So again, think of your service, your utility. You are a power company, you're a phone company. You don't want to have the power go out once a month. Or maybe it's good, you may want your cell phone to be off for an hour a month or maybe longer. But in general, we want you to design that it's up all the time. Series versus parallel, just at a high level, things that behave in series, the availability there is that the probability that everything is working at the same time. So let's say you have 3 things at 99.9%. The probability that all 3 of those are working at the same time is actually 97%. it's 99% to the third. Okay. So the key with items in series is that a chain is weaker than its weakest link. So no matter how many items you have together, you could have A and B be 4 nines, and you could have C be 2 nines. It's going to be worse than the worst one. Okay. So think of this again. Let's just say you've got to make a commute and you've got to go from a car to a train to a bus. What's the probability that all of those are on time? Versus parallel, the availability is a probability that all of those are non-functional. So it's a 1 minus the availability. So you can actually take 3 services that are not very available at 2 nines, but if they can operate in parallel, then your downtime goes up to, in this example, 6 nines. So a parallel system is redundant to the nth degree. Now, not all things truly behave this way, but this is the basic math that we're going to walk you through. Items that behave in series versus items that behave in parallel. And things don't truly behave in true parallel, but things do generally behave in series when you follow anti-patterns.
Philip,
This
could
is
you
one-
roll back just once?
Yeah.
Another element to look at it, and it's clear to see with the math, on the series side, if you put a fourth and a fifth in there, your availability goes lower and lower because you're adding a number to that exponent. It's going to 4 or 5 or 6. That same factor does not happen in the parallel side. The math changes, but it doesn't sizably change, and you're still at 5 or 6 nines tremendously. So parallel highly outperforms series.
The logarithmic reminders here, this is just a simple example. And the reason we show you this is that as you add more and more components, as Doug said, and this is really for the series, the availability of components in series, that you are basically adding those components together. With the example of base 10 log, if you have 10 to the second times 10 to the third, that's 100 times 1,000, just a simple reminder. But we're going to show you this math, why these exponents are important for you. We're going to skip this one, but this is one you can read if you understand, if it takes a long time to restore service. So for example, if your mean time to restore service is always an hour, no matter what the problem is, you can only have 1 outage a year in that case. If your mean time to restore service is a day that's a recovery, if you have 1 failure, a DR situation, you're not going to hit even 3 nines. You might hit 2 nines in that case. So that's why DR is important if your mean time to restore service is longer than a day. If you can get down to minutes, then you have a much better chance of being able to handle multiple failures in a year. We're going to walk you through why we claim it's very hard for a single service to have higher than 4 nines or 99.9%. So if you look at a single service, this is just a standalone thing. Think of it as your laptop. Think of it as a EC2 container at AWS or whatever you're managing. That particular box is going to have some subcomponents, right? It's going to have a NIC, an operating system, your DNS, memory, comm servers, storage, application. Just think of the things that break on your particular laptop or desktop at home. All of those have to operate in serial, right? If one is down, the entire service is down. So that means the availability is the product of all of those subcomponents. So let's assume all of these components here have 5 nines. Now, for most of you that have a laptop, you know that your operating system does not run at 5 nines. Very few applications that you run on your desktop run at 5 nines. But let's, in this example, assume that they can run at 5 nines. What would be the number of components you can have before it gets to 4 nines? Well, that's what the logarithmic math is here. Should mean you could have at most 10 components before you go from 5 nines down to 4 nines. But really, you get there at 8 components. When you do the math here, when you do 8 components, you're going to already be at 4 nines already. So that's how quickly you can degrade service. So that's just a single standalone service. So that's why it's very hard for one to achieve higher than 4 nines. But you have a calling service, and your calling service could be another service in your architecture. It could be your customer's browser. That thing is typically making at least 3 hops. Okay, it's going through a router, probably a load balancer, probably a switch. You could have something else in between there. So each of those has is basically its own little box, and it's running all those same components. So every time you have a call-in service calling another one, you need to take into account 3 more hops. So you actually need to bump up the exponent by 3. Okay. And that's why. Any questions about this? So just think about that. Anything calling another service. All right. So let's look at an example, an e-commerce example. A browser going over GIP, and you have a catalog, a search service, a shopping cart, a checkout, a payment, an order management. All of those are typically different components. And what we're showing here is that they're all calling a single database. This was real common when people would build out e-commerce platforms, pre-Shopify or even early versions of Shopify. Magento was built this way. They were all a single monolith. In this example, we're breaking apart those services. So in this example here, this is an anti-pattern. We're going to walk you through a lot of these. This is a database fuse anti-pattern, which means everything that is behaving that's connected here is operating like a call-in series. And manage them, think of them like they're all calling one another. The reason that can happen is, let's say something backs up on search here. Ultimately, that's going to impact the database. When that impacts the database, it impacts all others. So anything in this call chain here can cause a failure, which means you have to do the math on this as if all these are operating as if they're chained together like a Christmas tree set of lights. So looking at this here, when you add up all the boxes, this looks like 9 services, which is you take that original number of 4 9s to the 9th. This looks like it should be 99.92%, which is 6 hours of downtime. But remember, what's really going on is every one of these services is making at least 3 hops. So really, you've got 27 items here that are operating this way. So you've actually gone from 6 hours of expected downtime to 19 hours of downtime. A lot of folks don't understand the impact of each of those items. So as Doug mentioned, as you add more and more services operating as if they're in series, that bottleneck is that database. And again, the database will eventually get bottlenecked, but it could be anything else in that call chain will cause that problem. So the proper design to flatten this out is to actually give each one of these calling services their own database. This is why domain-driven design is very important. You ultimately have to split out these databases so they operate standalone. Now, the hard part is splitting up your architecture in order to do this the right way. But when you get to this design, though, you've reduced the call depth. And so you now have at most, vertically, if you just count any of these, you only have 12 you have to take into account. So you've gone from 19 hours down to 8 hours of downtime. So reducing the fuse reduces the number of services that behave in series. This math is real important because we're going to walk you through all these anti-patterns, and patterns to remediate them are about removing these dependencies between them. And we're going to introduce the concept of having libraries instead of other services. And the reason we like libraries is that they're actually on the box. It's not making all these network hops. It's fewer things that can fail. But that's the reason you're going to see this math here is why we're going to walk through all of these different anti-patterns and patterns. So it's the reduction in call depth here. And this is going to apply for all these anti-patterns. We're going to walk you through service-to-service calls, not just service-to-database calls. A lot of intense math there. That's really the bulk of this session's webinar. So I'm going to pause here. We're wrapping up a bit early, but questions for anyone that want us to walk through any of the math again, we'll give you all these slides. Even when I learned this, I had to go through this 3 or 4 times to walk through this. And we also have a blog post that walks you through all these details too, if you find that reading through this math is more helpful. So questions for the team. I promise it'll get more interesting. This is the most difficult math you'll do in all of our classes and all of our webinars.
No more exponents
Yeah, no more exponents.
and no more logarithms. That's always fun too.
Yeah. Question.
Christopher.
Yep.
Hey, thanks guys. The math's not too bad. I have a team that works in AI, so they get much crazier math than this. But my question is, it goes back to you were saying about you don't really learn this stuff in school, and a lot of times you're learning it on the job. What would be your advice for helping? Because like my engineers definitely don't understand availability that well. Like, what would be some of your advice in terms of like helping educate or level up your current engineering team to some of these concepts?
So we found you actually have to walk through these slides. Because each one takes a while and they might need to hear it, like I said, 2 or 3 times, because they probably have never thought about this. And to make it more engaging, take one of your services that you have today and try to start estimating that. And what would be the likely availability of one of your key services? So give them a problem to solve. Their mind's going to be already pretty busy just understanding the math. So you may have to pace this out. When we've taught this before, we've crammed all this into a few hours. That's why we're splitting this up over a few weeks. So maybe give them a day to understand just what we walked through over the last 45 minutes. And then later apply it to a problem that you have where it can help, where they can try to do the math themselves to estimate the availability. Because at some point, they're going to recognize some anti-patterns. And in some cases, you're going to be okay. But in most cases, you want to understand where things operate in series. Those are your things you are most risk. Those are things that are going to kill you from a downtime perspective. We found that this example is the best way we've taught. I also have a link on one of our blog posts. There is an example from a gentleman in Australia. He teaches this. He's helped a lot of utility companies, and he uses an example with the car example that I mentioned for you. Having different cars, and then he has some simpler math problems. He also has a spreadsheet that helps you try to solve some problems. So think of if you have a cellular network as your internet service for your home, and then you have a backup for a satellite dish, say, as your backup, which is a better investment for you based on expected downtime. So there's some simple math examples that can help you understand that. So that gets you comfortable with the math. But then in your case, you really want to have a problem that you need to solve. The more that you can solve a problem using this math, the easier they can apply the concepts. So I don't know if you've got some ideas in your architecture now that you're worried about, but it would take you a while to walk through it, but it shouldn't be more than a few hours over the course of a few days.
Great, thank you.
The first big struggle point will be for network engineers or for software engineers who consider themselves to be at 4 or 5 nines, disavowing them of that because math doesn't work that way. Once they get through it's not embarrassment, but just the realization that, wow, we're really not performing at 4 nines, the energy returns to try and find a way to get there. And that actually turns the negative of finding out the truth into really good energy to try and recreate the conditions that you want. Any other questions? I'm hoping that Eric, I'm sorry. Looks like Philip may have frozen. Yep, his Zoom just died. We're actually practicing redundancy here at AKF. This was something we were prepared for. He knew his internet was flagging when we started the webinar, and I was paralleling him all the way along through the presentation. Guys, if you have no questions, that's the end of today. We're actually 10 minutes ahead of time. Thank you so much for being here. We love having you guys with us, and we look forward to seeing you in a couple of weeks. We'll go through the software patterns and anti-patterns. Have a great weekend.
Thank you. Thank you, everyone. Thanks for another great session.
Absolutely.
Thank you.